And so, for this last one, my question to you is, what do you think is going on here? Why do you think for primes we can always do this?
Well, I guess just a very basic one is that we're always going to have even factorials.
So you always have numbers to pair.
Okay, good. Very good observation. So for primes, we always have numbers to pair. Other than 2, don't forget about 2. So we do have to check, is one factorial congruent to -1 mod 2?
Yes.
Okay. All right, so it works there. And for the odd primes, we always have an even number to pair. Odd primes always can make pairs. All right, what else can we say?
Well, our first and last numbers in the factorial seem to always create our -1.
Okay, so first times last equals -1 mod p. Okay, tell me why that's true.
Well, because you have the -1 mod p times the 1 mod p, so it's just going to get you a -1.
Okay, good. So we always have enough, we always have an even number when we're doing our odd primes to make pairs. The first and the last always give us the -1. And now that leaves a fairly challenging problem as to why can we always find pairings with all the other numbers that multiply to be 1.
Mod the prime.
Yeah, mod the prime. And this, I'll tell you, this is a hard fact. This is not at all an easy fact. But what do you think? There's some ideas that you have.
Well, so the fact that it's a prime and not just any odd number is probably important.
Okay, yeah, the fact that it's a prime and not just any old odd number. Let's actually let's explore that. Let's do 9. Okay. So we have 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. And can you see what this is, mod 9, without multiplying everything out?
It's 0.
Why?
Because you've got the factors of 9, you've got 2 3s.
Aha, we have 2 3s here. We have a 3 here, and then we have a 3 inside the 6. This is 0 mod 9. Okay, so when we don't have a prime,
it's always 0.
Well, we got to be careful about that. We do have to be careful about that. But when we don't have a prime, it's at least possible that it's not 0. So, for example, 4 is not prime. What is this?
That's gonna be. That'll be 2.
2 mod 4. Okay. Here we don't have all the factors of 4 because we only have 1, 2.
Yeah.
But probably for like the larger factorials,
so
have all the factors.
we want to see, so for 9 at least, we found that this is 0 and it's not -1. So can you see why we can't find pairs for the numbers that multiply to be either -1s and 1s? So let's see, like we do get 8 times 1 mod 9, which is -1. Maybe there's another pair that multiplies to be 1. Could we find something?
7 and 4.
7 and 4 gives us 28, so that's a 1.
And then, let's see.
So
Can you find a pair that's left that multiplies to be 1 mod 9?
So 5 and 2.
5 and 2. So we press it 8, 7, 5, 4, 2, 1. 5 and 2 gives us a 1.
Then you're left with 6 and 3.
Okay, and what's the problem with 6 and 3? Why can't 6 and 3 multiply to be 1
Well,
mod 9?
They multiply it to be 18, which is 0 on 9.
Okay. Why can't anything, any integer multiplying 3 ever be 1 mod 9?
Because 3 is always a factor of 9.
Okay, so what are the mods going to be
So-
when we look at multiples of 3 mod 9?
3, 6, or 0.
That's right. So you can see why it sort of breaks down for non-primes. We're going to have, for non-primes, we are going to have factors in here. And those factors aren't going to be able to produce a 1 when you multiply. But then, we can leave it here. There's something else about primes, and it's advanced, and it's a really special property that primes have. But it actually produces this amazing miracle that for primes, p minus 1 factorial is congruent to minus 1 mod p. And I have to say, until I saw this theorem last night, I actually even never noticed that.
Wow.
So, you know, we have 24 we looked at, even for 3 we get 2. And for 5 we get 4 factorial is 24. For 7 we get that 720. And then we saw it for 11 and 13. We tried it ourselves, and you just keep trying. You can always find those pairs, which is a pretty amazing property of numbers.
Yep.
Yeah.
All right, hey, good work this morning, guys. Good job.